All right, so the next section we're going to talk about is 3.6, the derivative of log functions. And there's two common log functions that you have seen, right, at this point. The first one, or the generic format, is something like this. Like you've seen log base 5 of 10x, for example, or log base 7 of 19, right? Your calculators have a log button. Remember, A signifies the base, and the U is what we're taking the log of. This A, remember, this is a subscript right here. This does not mean log of A times U. This is log base A of U. Now, how do we derive that? This is just a formula that you guys will have to remember. It's just 1 over U and then ln of A and then times du dx. So if you notice the chain rule is popping up again, the chain rule always pops up every single time. Whenever you derive some kind of function trapped inside of another, or a piece trapped inside of another piece, like this inside of a log, or u inside of a trig function, or u inside of an inverse trig function, we always had to take the derivative of u at some point, right? That was the chain rule right there. So where do we go from here? What's the other log that we're talking about? Well, it's this right here, right? Remember, what is natural log? That's just another very common log. If you recall, natural log of u is just equal to log base e of u. All natural logs were just a very special type of log. It just had the base of e, right? Remember, e is approximately equal to 2.71, blah, 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 with a bunch of decimals. But you also have a button on your calculator for natural log, right? Because it's a very common log that's used in lots of applications. What's the derivative of the natural log of u? This one's a little easier. It's just 1 over u times du dx, like that. So basically, natural log stuff, if we take the derivative, it's 1 over the stuff times the derivative of the stuff. It's a lot easier to remember than this one right here, because this one has that additional piece of, oh, it has the ln of a in the denominator. But as far as working both of these or deriving with both of these, it's not that difficult. Okay, so how do we do that, right? Like, let's just go back to this right here. Like, we want to find ddx of log base 5 of, say, x squared minus 9. Something nasty looking like that. I mean, it doesn't matter what it looks like, because you just need to identify what's the a, what's the u, and then derive it according to this equation right here. So the derivative of a log, right, is, if we follow it, it's going to be 1 over u. Well, what's the u in this case? X squared minus 9. ln of a in the denominator. What's a? 5, right? So it's ln of 5, still in the denominator, times du dx. Well, that's the derivative of your u. What's the derivative of x squared minus 9? It's just simply 2x, right? So then we're left with 2x over ln of 5 and then x squared minus 9. So what did I do? Remember, when we chained this right here, this is 2x over 1. And all I did was I just multiplied the numerators, and then I shifted this constant out in the front of this denominator right here. And that's how the logs work. Again, it doesn't matter how nasty or complicated it looks. Like if we had y equals log base 2 of, and I'll say 5x squared plus 3x minus 1. And we want to find the derivative, right? Y prime, that also means the derivative. Just a different notation. How are we going to do that right here? Follow the equation, right? It says, oh, derivative of log base a of u is 1 over u. So 1 over, this is our u component, 5x squared plus 3x minus 1 times the natural log of a. A was 2 in this instance, so it's natural log of 2. Drag this 1 out. And then times the derivative, right? The derivative of u. That's the chain rule, right? du dx. So what is the derivative of 5x squared plus 3x minus 1? That's going to be 10x plus 3. Derivative of any constant is 0. And this is all still over 1, right? Now, what can we do? What more can we do to this? We can just multiply, right? 1 times the top. This is 10x plus 3. On the bottom, we can just shift the ln of 2 out to the front. And there is your final answer. And of course, if you could simplify this further, like factor it or something like that and knock terms out, yeah, do so. But in this case right here, a lot of times with these log functions, especially these right here, when you derive them, you're just going to be left with something pretty big where you can't really simplify it. Now let's go on to the derivative of the logs, natural logs. Those are used more frequently. So remember, I'm just going to write that formula down again. Derivative of the natural log of u, that's 1 over u times du dx. So let's try this one out. Like let's say we have y equals 1 over, y equals ln of x cubed. So what would y prime be, or what would the first derivative be right there? Well, natural log is easier than the log one. It's just the derivative is 1 over the stuff times the derivative of the stuff. The stuff right here is the x cubed. So 1 over u is 1 over x cubed times the derivative of the u. What's the derivative of x cubed? 3x squared. All right. So this becomes 3x squared over x cubed. This we can definitely simplify, right? You got x squared up top, x cubed on the bottom. So you're left with 3 over x. That would be your derivative right there. So yeah, in that instance, we were able to simplify the expression. What if we had, say, y equals ln of the cosine of x? So the stuff this time, or the u, is cosine of x. Guess what? It still works the same way. We followed this derivative formula. So y prime is 1 over the stuff, or 1 over cosine of x, times the derivative of the inside, or the derivative of cosine of x. What's the derivative of cosine of x? Remember, it's going to be negative sine of x. As far as simplifying, what can we do? We can say, oh, this is negative sine of x over cosine of x. And then furthermore, we can say, oh yeah, isn't sine over cosine tangent? It sure is. So this ultimately becomes negative tangent of x right here. What if we had y equals natural log of the 5th root of x? Let's do that. So how do we do that? Remember, how do we derive with radicals? What was the first thing that we do before we even start the derivation? We convert the radical into root form. So this is actually the natural log of x to the 1/5 power, right? Like that. Now we're going to do our 1 over the stuff times the derivative of the stuff. Remember, the reason why we're converting this from radical form to exponential form is because that's how we derive, right? We have to use the power rule. Power, exponents are powers, right? So how do we do that? Well, this is going to be 1 over, not equals. So now y prime is going to be equal to 1 over the stuff, which is just x to the 1/5, times the derivative of the stuff. What's the derivative of x to the 1/5? It's 1/5, right? And then x to the, and then we do 1/5 minus 1, which is negative 4/5. Now, how do we simplify this right here? Well, this 5 is in the denominator, correct? So we could say, oh, well, I have 5x to the 1/5, and I still have the 1 up top. But this x to the negative 4/5, what can we do with that right there? Well, we can make it positive, right? How do we make that positive? We flip it to the bottom. So now we have this. We have 1 over 5x to the 1/5 times x to the 4/5. What happens when you multiply similar bases? What do you do with the exponents? You add them. So what is a fifth plus 4/5? It's 5/5, right? But then isn't 5/5 1, right? So your answer is actually 1 over 5x to the first. That's your first derivative right there. So these are kind of nice because you can see, oh yeah, they're quicker than the other ones. They're not as tedious as the other ones as we were doing. But what if we have now like natural log of the sine of x cubed? So the stuff now, all this, right? You may be wondering, what's the u? All this is the u. All that, because that's basically what's inside of the natural log. All that stuff inside the natural log is the u. How are we going to derive that? That's just going to require a lot of chaining, right? Chain rules coming up. Can't forget it. So if we want to take the first derivative, well, how do you take the derivative of natural log of something? It's 1 over something, so 1 over sine of x cubed times the derivative of the stuff, or times the derivative of sine of x cubed. Remember, this is the chain rule. This is not the product rule. This is not sine of x times x cubed. It's sine of x cubed. So what we need to do is, remember with the chain rule, you derive the outside first. What's the derivative of sine of x? It is cosine of x. Or in this case, we have cosine of x cubed. Now that we've derived the outside, we need to derive the inside. What's the derivative of x cubed? It is 3x squared. 3x squared right there. So if we multiply this out, right, like we have 3x squared cosine of x cubed over sine of x cubed. Can we somehow rewrite that? Yeah, right, because sine of, or cosine of x cubed over sine of x cubed, what does that give us? Remember, sine over cosine is tangent. So cosine over sine would be cotangent. So in reality, this is 3x squared and then cotangent of x cubed. So that would be your answer in that instance. What if we had something like this, like y equals tangent of ln of x squared? So kind of like a reverse situation of this one, right? So we have the trig function first, then the natural log. How do you work that? Chain rule this time. It's still chaining, and then we're going to have to derive the natural log at some point. This is not product, right? You're not going tangent times natural log. You're taking the tangent of the natural log of x squared. So since we're chaining this thing, we start with the outside. What's the derivative of tangent? Secant squared. So you have secant squared of the inside. The inside's been left alone. So we chained the outside. Now we need to look at or focus just on the inside. What's the derivative of just natural log of x squared? Well, natural log of stuff, right? The derivative of natural log of stuff is 1 over the stuff times the derivative of the stuff. This is the u, right? If you want, label that thing. Anything trapped inside of the natural log, that's the u right there. So continuing with this, we have, remember, natural log of x squared, we're chaining that. We're deriving that component right there. That becomes 1 over x squared, right? Because we're following this formula, times du dx, or the derivative of the u, which is 2x. So what's left over, right? What is left over right here? Well, 2x over x squared, we can kind of simplify that, right? One of these x's gets knocked out. The 2 is still in the numerator. So that's equal to 2 over x. That's what's left over from here, right? This, I'm just throwing it right up here once you simplify it. And then we still have the remaining secant squared of natural log of x squared. So in this case, we had to do chain rule first. So we derive the outside, right? That's where the secant squared came from. Nothing else changes in the problem. And then you move to the next innermost, the natural log of x squared at this point. So the derivative of the natural log of x squared was, remember, 1 over x squared times the derivative of x squared. This little piece comes from us following this formula right here, right? The natural log of u. What if we had y equals sine of the ln of 1 over x, something like that. So very similar to this one, right? Got the trig function first, then the natural log of whatever. Before we start this, though, I'm going to rewrite this and say y equals sine of natural log of x to the negative 1 power. Why did I do that? Because now we can use the power rule, right? It's a little easier to work out. I just flipped up the exponent. If this was 1 over x to the 5th, you could say x to the negative 5, right? That just makes it a little easier to derive. How do we start this? We do the chain rule, right? We have to derive the outside first, which is sine. So the derivative of sine is cosine. Nothing else changes within the rest of the problem, so we still have natural log of x to the negative 1. Now we needed to derive natural log of this stuff. So remember, the derivative of the natural log of stuff is 1 over the stuff times the derivative of the stuff. The stuff in this case is x to the negative 1. So 1 over the stuff. So that's 1 over x to the negative 1 times the derivative of the stuff, which is x to the negative 1. What's the derivative of x to the negative 1? It's negative 1 x to the negative 2, right? Because you're going negative 1 minus 1 to get this negative 2 power. Now, to simplify, what can we do? Well, look at this component right here, right? Like, yeah, it looks kind of weird because we have an x, we have two x's, both of negative exponents. How should we simplify that? Let's make them both positive, right? So I'll just work this off to the side right here. 1 over x to the negative 1 becomes x to the positive 1. This is still negative 1 right here, but this x to the negative 2, if we flip it, it becomes positive, and we get this. So this is what you have left over if you were to make both their exponents positive. Now, what's left right here when you simplify it a little further? Well, negative 1 is still up top. How many x's do we have left over? You have 1 up top and 2 on the bottom. So you're going to have 1 left over, and it will be on the bottom, right? So all this right here simplifies into negative 1 over x. What is our final answer going to be, though? Well, I'm just going to drag this out to the front and say negative 1 over x, and then cosine of ln of 1 over x. I just flipped this exponent and made it positive again, just like that right there. Okay. You could have left it like this, x to the negative 1, but normally we want to keep our exponents positive, so that's why I flipped it to make it positive like that. What if we had y equals x cubed natural log of 8x? Now this says x cubed times ln of 8x. times. What does times mean? Product rule. Got to do the product rule right here. So this is our F, and this is our G. G, F. Let's work it out. Remember, the product rule is FG prime plus GF prime. So F times G prime, that's going to be X cubed. G prime, what's G going to be right here? Or the derivative of G. Remember, it's 1 over the stuff, or 1 over 8x, times the derivative of the stuff, or times the derivative of 8x, which is just 8. So what do we have that's left over? Oops, I'm forgetting something. I'm jumping ahead. That was F times G prime. Then we have plus G F prime. That's natural log of 8x. F prime is the derivative of x cubed, which is 3x squared. Now let's clean this thing up. What can we do? Well, let's check this out. These 8's can reduce. The x cubed and the x, this is x the first, that can partially reduce, right? That will partially reduce to x squared, right? Because if you have 3 x's up top, 1 on the bottom, you're left with 2 up top. And then plus, what's left over right here? Just the 3x squared ln of 8x. And again, you normally want the variables first, right? Number of variable, then the log stuff or trig stuff when we're writing out our final answers. Now, what if we had something like this? And we had to take the natural log of this obscene function right here. It is true that we could do, 1 over the stuff times the derivative of the stuff. But if we took the derivative of the stuff, this is a lot of work, right? Because it's x cubed times this root. So we have to do product rule, go out there and rewrite this in, radical form and stuff like that. But a trick to use is whenever you're multiplying or dividing with natural logs, meaning you have multiplication or division of multiple terms inside of a natural log and you need to derive it, what you should do is expand them with the properties of logs. Remember, there were 3 properties from the logs. This comes from algebra. Okay, like if you had log of, say, a times b, that's just log of a plus log of b. That was called the product rule. Or if you had log of a divided by b, that's the quotient rule. That's equal to log of a minus log of b. And then we also had the power rule. So like if we had log of a to some power of b, like this, we could say that's equal to b log of a. So here are the 3 rules. 1, 2, 3. This third one was called the power rule because it basically dealt with the exponent. The power rule says you can shift that exponent out in front of the log right here. So product, because you're multiplying, quotient, you're dividing, power, because you're dealing with an exponent. Really important with the quotient rule, the second one, it's log of the top minus log of the bottom. Again, these 3 rules you all should know, right, from algebra. If you took Math 130 at Delgado, you definitely did this towards the end. So how do we go about expanding this one right here? Well, this is going to involve the product rule and the power rule, basically rules 1 and 3. When are we going to use the third rule? Well, remember, if you have radicals, you got to rewrite them in exponential form. Remember, this is 1/2. Why? Because what's the index of that root right here? It's 2. If they don't give you anything, it's an automatic 2 right here. It's not because this is 2, it's because that was 2 right there. That's where that 1/2 comes from. Now, if we expand it, this becomes y equals ln of x cubed plus ln of x squared plus 1 to the 1/2 power. So you see, I applied just the product rule, rule number 1 right here. I broke it apart into 2 smaller logs. Now we don't have to do the product rule right here, okay? Because again, we were able to break it apart from its initial state. So that's me doing rule number 1 of the product rule, expanding via the product rule of logs. Then I can take it one step further, right? By doing the power rule. Remember, the power rule is number 3. It said, oh, if you have some kind of exponent, you can take them and throw them out in front of the respective log. We haven't derived yet, okay? We're just expanding. The reason why we're expanding this right here is that it's easier to take the derivatives of these logs. If we look at these 2 logs, smaller logs, it's way easier than trying to take the derivative of this initial one right here. We could have taken the derivative initially, like I said, from the get-go, but it's like you'd have to say 1 over all this times the derivative of all this right here. To derive this in its current state, it would be a pain in the ass. But if you break it apart with the properties of logs, look, now it's super easy, right? It's just 1 over the stuff times the derivative of this stuff. The stuffs in these natural logs are way easier because it's just one little thing. They don't even have powers because we moved them out to the front. So how are we going to do that, right? So let's find that derivative right there. So for the first one, 3 ln of x. Well, the 3, we just bring it along. What's the derivative of natural log of x? It's 1 over x times the derivative of the x, which is 1. And then we move on to the next one, plus 1/2. And then derivative of natural log of x squared plus 1. It's 1 over x squared plus 1 times the derivative of x squared plus 1. What's the derivative of x squared plus 1? It is 2x. Now let's clean it up, right? We have y prime equals 3 over x plus, and what can we do right here? Well, we can knock out or reduce these 2's, and you're left with x over x squared plus 1. So that is your derivative of that expression right there. So with those 3 rules, the product rule of logs, the quotient rule of logs, and this power rule, you can do or derive any kind of log function, no matter how nasty it looks. Like what if we had y equals, say, natural log of the sine of 2x over x plus 1 cubed. So yes, you could do 1 over the stuff times the derivative of the stuff, but imagine that you'd have 1 over the sine of 2x over x plus 1 cubed times the derivative of this thing right here. So you have to do this huge quotient rule, right? That's what will pop out of that as you're chaining it. Or the easier way is to expand it using the properties of logs, okay? So since this is the quotient rule for logs, remember it's log of the top minus log of the bottom. So this is y equals natural log of sine of 2x minus natural log of x plus 1 cubed. So a little easier to work out, right? So remember, log of the top minus log of the bottom. And remember, when you're using the product or quotient rule, you will have multiple logs. A lot of people will say, oh, it's natural log of sine of 2x minus x plus 1 cubed. No, you also need to apply that natural log to the x plus 1, okay? Anytime you have an expanded new piece, whether it's product or quotient, you're always going to have another ln, another ln. And there's one more thing we can do, right? The power rule right here. Take that 3 and throw it out in the front. So we have y equals ln of the sine of 2x minus 3 ln of x plus 1. So let's go ahead and try to find the derivative now. So what is the derivative of the natural log of sine of 2x? It's going to be 1 over the stuff, or 1 over sine of 2x, times the derivative of sine of 2x. Well, what's the derivative of the sine of 2x? It's cosine of 2x, and then times the derivative of 2x, which is 2. Remember, that was the chain rule, right? We had to derive the outside chunk, which was derivative of sine, which is cosine. And then we had to derive the inside chunk afterwards, which we were left with 2. And then we have minus 3. And then what's the derivative of ln of x plus 1? It's 1 over x plus 1 times the derivative of x plus 1, which is just 1. Now, how can we write this? Well, we have the 2. And then we have cosine of 2x over sine of 2x. Remember, cosine over sine is cotangent. So this is cotangent of 2x. And then minus 3 over x plus 1. Just like that. All right, now what if we had, why is it important to have logs, right? Like, why are we learning about logs or derivatives of logs? What if we have something weird looking like this? Now we have x's everywhere, right? We have an x at the base. We have an x at the exponential level. What do we do, right? What do we do right here? And we sort of had this issue in the algebra courses, right? Sometimes you had x's trapped up inside within the exponent. So we had to get them out of the exponent. How do you get x's out of the exponent with natural logs? So we're going to take the natural log of both sides. Why did we do that right there? Well, remember that third rule with the logs, what was that? It was the power rule. What did that let us do? It let us take the power and move it out in front of the log. So now we could say, oh, this is natural log of y equals cosine of x times the natural log of x. Well, that's a little better because remember, we're trying to find the derivative. And now all our x's are on the base level, meaning they're not exponents anymore. So how do we derive this right here, right? What do? Well, we take d dx, right, of both sides. Now, what's going to happen here? Well, now we have natural log of y that we're taking the derivative of. So remember, it's still 1 over the stuff times the derivative of the stuff, but this is not natural log of x. This is y. So when you're taking the derivative of y, remember what's going to pop out. You're going to have, this is the implicit differentiation, right? So we're going to have a dy dx that pops out of this. We're still going to have 1 over y, though. So remember, the natural log of stuff, or the derivative of that, is 1 over stuff times the derivative of the stuff. And then equals, remember, where did this come from? Remember, the derivative of natural log of stuff is 1 over the stuff times the derivative of the stuff. Your stuff in this case was y, so it's 1 over y times the derivative of y with respect to x, which is dy dx. What about the right-hand side, though? It all has x stuff. And we're multiplying. What does that mean? Product rule, right? What does that leave us with? F times g prime. All right, so that's going to be cosine of x times the derivative of natural log of x. That's 1 over x times the derivative of x, which is 1. That's f times g prime plus g times f prime. What's the derivative of cosine of x? It is negative sine of x. Let's clean this up. So we have 1 over y dy dx equals 1 over x cosine of x minus natural log of x sine of x. We're not done yet because remember we're looking for dy dx, right? All in terms of x. We still have this 1 over y with it. How do we get rid of this 1 over y? Well, we multiply both sides by y, right? Remember, anytime you got to move a fraction or get rid of a fraction and you have an equation, you multiply both sides by that denominator, which is y in this case. In doing so, this gets knocked out, and we have dy dx equals y times basically all this stuff right here. And we're almost done. I know people are like, what? We're not done yet? Yeah, we're not done yet because our derivative has to be all in terms of x, right? We still have this y right here. We have to somehow convert this y into some relationship involved with x. How are we going to do that? Remember, we started with y equals x to the cosine of x. So we're going to have to substitute this back into here for that y. So your ultimate answer or your derivative is x to the cosine of x times all this right here. Remember, this became this because we had that initial relationship of y equals x to the cosine of x. Don't forget to do that one little step. Your derivative cannot have any y's floating in there, okay? When you're doing this log trick, everything has to be in terms of x. So this is a very tedious problem, but what's nice about it is they all work out the same way. It's the same types of steps, okay? Just take your time with them. Let's try another. What if we do it like sort of the reverse way? Instead, let's try y equals tangent of x raised to the x power. A little different, right? Last time we had the x and then the trig function was in the exponent. Now I flipped it, right? Flipped the script. But guess what? Still works the same way. What do you do first? You take the natural log of both sides. Ln of y equals ln of all this good stuff right here. And then from there, what happens next? Why do we do that? The power rule. We can take this x and shift it down in front right here. So now we have ln of y equals x times ln tangent of x. And then from here, what do? We derive. So we're going to take the derivative of both sides. This marker is dying. Now remember, what happens when you take the derivative of y with respect to x? You're going to have a dy dx that pops out. So the derivative of natural log of y is going to be 1 over y times the derivative of y, which is dy dx. And that's equal to, how are we going to derive the right-hand side? Product rule, because you have f times g this time. So f and g, remember product rule is fg prime plus gf prime. So f is going to be x. What's the derivative of g? Well, what's the derivative of natural log of tangent of x? Remember, that's going to be 1 over the stuff, or 1 over tangent of x, times the derivative of tangent. What's the derivative of tangent? Secant squared of x plus gf prime. That's going to be natural log of tangent of x times, what's the derivative of f, or what's the derivative of x? It is 1. Now, continue on from this line right here, right? So far, we took the derivative. Remember the natural log of y, the derivative of that with respect to x is 1 over y times the derivative of y with respect to x, which is dy dx. On the right side, what happened right here? We had to do the product rule, right? Because we had x times ln of tangent of x. So f times g prime, that's x times the natural log, or the derivative of the natural log of tangent of x is 1 over tan x times the derivative of tangent of x, which is secant squared. Then plus g times f prime. G is ln of tan x. F prime, or the derivative of x, is 1. Let's go out there and keep going, right? Can we rewrite secant squared over tangent of x into something else? Like if we look at this right here, can we simplify this? Like, does it reduce to maybe cosine or tangent or something or whatever? Let's just work that off to the side just to see. So secant squared x over tangent of x. Does that reduce to something? Well, how can we figure it out? Let's break everything down in terms of sine and cosine. This is 1 over cosine squared of x over sine x over cosine of x. Remember, secant squared is just 1 over cosine squared. Tangent is sine over cosine. This, if I rewrite it, is just 1 over cosine squared of x times cosine of x over sine of x. It's getting kind of sloppy. But what can we do with that? We can, I'll put it down here. I know everything's all over the place. I just don't have enough space. These cosines, one of them can cancel out. So you're left with 1 over cosine of x. And then that sine of x is still left on the bottom right here. So this basically becomes cosecant x secant x, or rather secant x cosecant x. So when you flip the cosine up, it becomes secant. When you flip the sine up, it becomes cosecant, like that. So now we have 1 over y dy dx equals x, and then secant x cosecant x plus the natural log of tangent of x. We're not finished, right? Why? Because we need to get dy dx by itself. How are you going to do that? Multiply both sides by y. Now we have dy dx equals y times x secant x cosecant x plus natural log of the tangent of x. Remember, when you're doing these types of problems, you always have y times all that stuff on the right hand side. So watch the parentheses right there. It's not just into the first term. And then to finish it off, remember our derivative has to be all in terms of x. We have this y right here. What's the relationship between x and y that we had? It was the initial problem, right? Remember, we had y equals tangent of x raised to the x power. So what are we going to do? We're going to take this, right? We're going to plug this in for that y right there. So ultimately, finally, we have dy dx equals tangent of x raised to the x times all this other stuff right here. You will always do this last little step where whatever your initial problem was, you're going to take that relationship and substitute it back into that y. That y component, that will always happen whenever you do this special differentiation with the logs right here. So don't forget to do that part. You cannot leave your answer like this right here. It all has to be in terms of x for this derivative. But remember, you always have that relationship between y and x. It's the problem that you started with. So you have to go back in and substitute that back in. And don't forget your parentheses around that entire other segment, okay? So that concludes section 3.6.